Hi everyone, welcome to NCC channel. My name is Naresh, chemistry lecturer. Today I would like to discuss some important properties of third A group elements. Some important properties of third A group elements. Third A group elements I have taken boron, aluminum, gallium, indium, thallium. Boron, aluminum, gallium, indium, thallium. Now coming to atomic number. There is no need to remember these atomic numbers. I will give a sequence. If you remember this sequence, you can write atomic numbers of any elements. That sequence is 8, 18, 18, 32. If you remember this sequence, you can write atomic number of any element. Now the condition is this sequence should be second period elements only. This sequence should be added to second period elements. Now boron atomic number is 5 and it belongs to second period element. Now add 8 to this 5. So 5 plus 8, 13. Now add 18 to this number. 13 plus 18, 31. Now add 18 to this number. 31 plus 18, 49. Now add 32 to this number. 49 plus 32, and that is 81. So in this way we can write atomic numbers easily. Now coming to electronic configuration. There is no need to worry about to write electronic configuration. There is a simple trick to write electronic configuration. I will give the trick. First you have to write noble gas elements: helium, neon, argon, krypton, xenon. And next these third A group elements belongs to these belongs to third A group elements, and that means the valence electronic configuration of third A group elements is ns2 np1. Now boron belongs to second periods. Now boron belongs to second period elements. Can we write 2s2 2p1? 2s2 2p1? Yes, we can write, because boron belongs to second period. That's why you can write 2s2 2p1. Now neon 3s2 3p1. Gallium 4s2 4p1. Indium 5s2 5p1. In thallium 6s2 6p1. Now in gallium, before 4s2 4p1, there are 3d electrons present. In indium, before 5s2 5p1, 4d10 electrons present. In thallium, before 6s2 6p1, 4f14, 3d10 electrons present. So in this way we can write electronic configuration in easy way. Now coming to atomic radii. Generally from top to bottom atomic size increases. That's why atomic radius also increases. Now the atomic order is boron, aluminum, gallium, indium, thallium. But there is a small change takes place in this sequence. So that is gallium has less atomic size compared to aluminum. Because when you observe the electron configuration of aluminum and gallium, aluminum has no d electrons, but gallium has d electrons. Already you know that d orbitals are 4 shielding orbitals. So the shielding order is s, p, d, f. So d and f orbitals are pure shielding orbitals. Due to pure shielding of d orbitals, the nucleus of gallium can attract valence electrons with I force. That's why the size decreases. So that's why gallium has less atomic size compared to aluminum. Now the correct order is boron, gallium, aluminum, indium, thallium. So this is the correct order of atomic radii. Now coming to ionization energy. So ionization energy is inversely proportional to atomic radius or atomic radii. So atomic radius increases, ionization energy decreases. Now boron to thallium atomic radius decreasing, though. So boron to thallium atomic radius increasing, so ionization energy decreases. Now boron has high ionization energy, followed by gallium, followed by aluminum, followed by indium, followed by thallium. But there is a small change takes place in this sequence in between indium and thallium. So when we observe the electronic configuration of thallium, it contains 4f and d orbitals. F and d orbitals. Already you know that d and f orbitals are four shielding orbitals. So due to four shielding orbitals, so the nucleus of thallium can attract valence electrons with I force. So that's why to remove valence electrons, it takes high amount of energy, that is ionization energy. So ionization energy is more for thallium compared to indium. So that's why the sequence should be changes like this: boron, gallium, aluminum. After that, thallium comes. Thallium has more ionization energy compared to indium. This is the correct sequence, correct ionization energy of third group elements: boron, gallium, aluminum, thallium, indium. This is the ionization energy sequence. Now coming to melting point and boiling points. Boron has high melting point and a high boiling point. This is one of the important question. In third group elements, which elements can show high melting point and a high boiling point? That is boron. Due to three-dimensional network structure, it has a high boiling point and a high melting point. Now when we are moving from top to bottom, boiling point decreasing and melting point also decreases. But in melting point, boron to gallium decreasing takes place, and gallium to thallium slightly increasing takes place. Now coming to gallium. So gallium melting point is 303 Kelvin, that means 30 degrees Celsius. 30 degrees Celsius. So that means it exists as a liquid in summer season, and in remaining season it can exist as a solid. That's why gallium also called summer liquid. Because in summer season it exists as a liquid. In remaining season it can exist as a solid. Now observe boiling point. Boiling point is 2676 Kelvin. And when we observe the difference between melting point and boiling point, so the difference between melting point and boiling point of gallium is 2373 Kelvin. So this difference is more for any element. So that means gallium exists as a liquid, long range temperature, it exists as a liquid. That's why gallium is used in high temperature thermometer. So it is also one of the important question. So which element is used in high temperature thermometer? That is gallium. Gallium is used in high temperature thermometers. Now coming to nature of oxides. Third group elements can exhibit E2O3 oxides. So third group elements can form E2O3 type oxides. So boron can form B2O3, aluminum can form Al2O3, gallium can form Ga2O3, indium can form In2O3, and thallium can form Tl2O3 oxides. Now coming to observe nature of oxides. B2O3 is acidic nature. It has acidic nature. And aluminum oxide and gallium oxides are both are amphoteric nature. So amphoteric means these can react with acids as well as bases. That's why these are called amphoteric oxides. Now indium oxides and thallium oxides are basic nature. These are basic nature. So these are the nature of oxides. Now coming to boron. It can show anomalous behavior because due to its small size, and it has high ionization energy and high electronegativity and absence of d orbitals, it can show anomalous behavior. That means it can form only covalent compounds. Remaining elements can form covalent compounds as well as ionic compounds. Now it can exhibit allotropy. But remaining elements does not show any allotropy. Now it is a non-metal. Already you know that it is a non-metal. So remaining elements are metals, and it has high melting point and high boiling point. Remaining elements does not have high melting point and boiling points. So this is the anomalous behavior of boron. So in this way we can explain the properties of third group elements. I hope that all are understood this concept. Thanks to all for watching my video.